Okay, so I asked you guys to study for your final. If you come across any questions that you need help with, you could send me an email. These could be questions that you come across from your book or from your old exams. And I will go over them, post up videos, and you can review them. So a student asked me to go over problems 4, 5, and 7 from exam number 3. So again, I'm going to write your final by taking out 4 problems from your old exams, making up problems similar, not the same problems, but similar to the ones on your old exams. And then that will be your final 16 problems, 4 from each exam. And so please don't send me an email asking me to do every problem from every exam. I will do what I have time for. If you keep it down to 3 per email, then we'll be good. But people are asking, so the student asked me to do problems 4, 5, and 7 from exam 3. That's what we're going to go over on this video. And so here we have problem number 4 from exam 3. Find the intervals on which the function is increasing and decreasing. Okay, so one of the things that you need to practice is reading the problem, understanding the problem, and then answering what I asked, not just spewing out everything that you've learned in this class on a problem. So all this is asking is find the intervals on which the function is increasing and decreasing. So to study for this exam, you shouldn't just try and cram all this, memorize it. You should understand it, right? So the question is, where is it increasing and decreasing? So you should ask yourself, what tells me if the function is increasing or decreasing? And what tells you that is the sign of the first derivative. So first we need the first derivative. Polynomial functions, sums of power functions, basic first derivative, 12x cubed plus 12x squared minus 24x, and the derivative of 2 is 0. Now, we want to be able to look at this and this expression and see where it's positive and negative. That's hard to do by the way it's written. It will be easier to do if we factor it. So if we factor this, we can begin by factoring out a 12x, and that will leave then x squared plus x minus 2. That's better, but we can factor it some more. And we leave that 12x alone. And then we have x plus 2, x minus 2 is how that factors. Okay, so there's your first derivative. And now we want to make the sign chart. This is the work I showed you. This is the work I expect to see. This is the sign chart for the first derivative, so you should label it first derivative. On your sign chart, what goes on your sign chart is the zeros of the derivative, or where the derivative is undefined. Those are called the critical points. So the critical points are what go on your sign chart, but nothing makes this undefined since the domain is all real numbers. And so from the first factor, we get 0. From the second factor, we get -2. And I just realized that I made a mistake. X plus 2, this should be x minus 1. And the 2 times the -1 is minus 2, which gives us that. And the 2 plus the -1 gives me 1. So that's right. And 1. And so these are my critical numbers, the numbers that make the derivative 0. There are no numbers that make the derivative undefined. Once we go to the left of 0, -3, -4, if we substitute them into the first factor, we will get a negative value. Substitute them into the second factor, we will get a negative value. Substitute them into the third factor, we will get a negative number. And when we multiply all 3 of those together, you will get a negative number. So negative times a negative times a negative is going to be a negative. That will work for any number less than -2. Once you get past -2, this x plus 2 will change sign. So when you put in -1, this will no longer be negative. It will now be a positive number. But the other 2 will still be negative. Only that one changes. So now you will have 2 negatives and a positive. When you multiply all that together, you will get a positive. until you get past 0. And once you get past 0, this one changes, right? So when you put in a negative number into the expression 12x, you get out a negative number. When you put in a positive number into the expression 12x, you get a positive number. And so now you have two positives and a negative. So then you will now get negative outputs. Your first derivative will be negative, right? And then once you get past 1, this last one switches. And now you have 3 positives. And when you multiply 3 positives together, you get a positive. And so the sign chart tells you where your first derivative is negative and positive. And if your first derivative is negative, the slopes of your tangent lines are negative. That means then that your graph is decreasing. If your first derivative is positive, your graph is increasing. So for decreasing, we see that this will be decreasing from negative infinity to negative 2, including the negative 2. For increasing, once we get past the negative 2, my original functions, my derivative is positive, so my original function will be increasing from negative 2 to 0. From 0 to 1, it's decreasing, so over here we put that with the decreasing union, 0 to 1. And then once we get past 1, we go back to increasing all the way forever and ever. It will never turn back around. It is just going to continue to decrease. Okay. So find the intervals on which the function is increasing and decreasing. It's decreasing from negative infinity to negative 2, union from 0 to 1. Increasing from negative 2 to 0, union from 1 to infinity. And that's it. That's all you were being asked to do. Move on. Find any relative extrema, right? So what tells us whether we have a relative extrema is either the first derivative test or the second derivative test. The second derivative test requires us to use the second derivative, but the first derivative test requires us to use the sign chart. We already have the sign chart. Why start over? So on your test, no need to remake the sign chart. You can reuse the sign chart from the previous part. Yeah, from negative 2 to 0, and then from 0 to 1. And this was negative, positive, negative, and then positive. And you can see that this is telling you that the graph is coming down and then it's going up. So it should make sense that you have a relative min at x equals negative 2. And when I ask for the relative extrema, I'm asking for the output of f of negative 2. And you can put your original function into your calculator, and at negative 2, you get negative 30. Then you have a, then you were going up and then down at 0. So then you have a relative max at x equals 0 of f of 0. And when you plug in 0 into your original formula, you get 2. And then you can see that you were going down and then up until you got to 1. You were going down, and then at 1, once you got past 1, you started going up. So that should make sense that you have a relative min at x equals 1 of f of f of 1, which is negative 3. And there you go. Find any relative extrema. We have 2 relative mins, 1 relative max, and there we go. We move on. Find the intervals on which the function is concave up and where it is concave down. Right? So again, what tells us concavity? The second derivative. So we had the first derivative was 12x cubed plus 12x squared minus 24x. Our first derivative was 12x cubed plus 12x squared minus 24x. And so then the second derivative is 36x squared plus 24x minus 24. And so then again, we can see that we have a factor of 12 in there. So we can factor out the 12. And that leaves 12 times 3x squared plus 2x minus 2. Okay, so when we try and factor this, only way you're going to get the 3x squared is with a 3x and an x. The only way you're going to get a minus here is with a plus and a minus. And the only way to get 2 is with 1 and 2. And so if I put the 1 here and the 2 here, then I will get from these two, I will get x. From these two, I will get minus 6x. And that does not work. And if I switch it and put the 2 here and the 1 here, then from these two I will get 2x, and from these two I will get minus 3x, and add those and I will get minus 1x. I never got the 2. So it's not possible. It doesn't factor. You can calculate the discriminant and you will see that it does not factor. The critical numbers for this one cannot be found just by factoring like we did in the first one. But you have a quadratic, and you can find the zeros of this using the quadratic formula. So then x is equal to negative b plus or minus the square root of b squared minus 4 times 3 times negative 2, all divided by 2 times 3, which is 6. So negative 2 plus or minus the square root of 4. 4 times 3 is 12, times negative 2 is negative 24, minus negative 24, which is going to be positive 28, all divided by 6. This is a real number. It's just not a nice rational number. It does have a spot on the number line, right? And so then you have two numbers. They're not critical numbers because the critical numbers are where the first derivative is 0. But you have two numbers that make the 0. Negative 2 minus the square root of 28, all divided by 6. And negative 2 plus the square root of 28, all divided by 6. And you're going to make the sign chart for the second derivative. Find the intervals on which the function is concave up and where it's concave down. What tells you whether a function is concave up or concave down is the sign of the second derivative. Right? Now, just by looking at this, you should know that the graph of this is a parabola that opens up. So then as you move further and further to the left, it's going to be positive. And as you move further and further to the right, it's going to be positive. And so then in the middle, it's going to be negative. And so there's the sign chart. So you could plug in numbers if you like, or you could look at the graph, whatever you choose. You could get a decimal approximation for negative 2 minus the square root of 28 divided by 6, and that's negative 1.21. This is approximately negative 1.21. And when you have the plus, you get positive 0.54. And so then you could pick something less than -1, like -2. You could pick something in between, like 0. And then you could pick something bigger than 0.54, like 1. And you can get your sign chart that way. But you should be familiar with what the graph of a quadratic function looks like. And that's what you get right there. Don't forget to answer the question. Find the intervals on which the function is concave up. So wherever it's positive, it's concave up. Wherever it's negative, it's concave down. And wherever it's positive, it's concave up. Okay, so then concave up on the interval from negative infinity to -2 minus the square root of 28, all divided by 6. And we don't include the endpoints for concavity. Union, it's also concave up over here on the interval from -2 plus the square root of 28, all divided by 6 to infinity. And then it's just concave down everywhere in between. -2 minus the square root of 28, all divided by 6, comma, -2 plus the square root of 28, all divided by 6. That's where it's concave down. The next question is asking for the inflection points. It's asking for the inflection points, right? And so I want the point. And so an inflection point is where the graph changes concavity to the left of -2 minus the square root of 28, all divided by 6. It's concave up. To the right, it's concave down. So there's an inflection point at that x value. Same thing with the other one. So -2 minus the square root of 28, all divided by 6. So then -2 minus the square root of 28, all divided by 6, comma, and we can figure out the y coordinate. We can get an approximation for it by plugging that into the formula. Okay, so -2 minus the square root of 28, all divided by 6. My calculator is telling me 0. Oh, no. I have the wrong one. I'm sorry. -16.36. And then I have -2 plus the square root of 28, all divided by 6. And that should be -0.6793. Okay. And so with that information, we can now make a accurate graph, right? And so that is our next problem. Graph the function, right? So the table of values that I expected to see was you using summarizing what you learned in your previous parts. We had relative extrema at -2, and we got -30. And we had relative extrema at 0 and 2, and then another one at 1, -3. And at negative 1.215, we had an inflection point of negative 16.36. And then at 0.5485, we had an inflection point of negative 0.6793. So these are my inflection points. These are my relative extrema. Okay. So then there's negative 1, negative 2, 1, 2. All the interesting behavior seems to be going on about there, right? But we got to get all the way down to negative 30. And so then we can go up by 5, 10, 15, 20, 25, 30. And then over here we'll go 5, 10, 15, 20, 25, 30. Okay. So then at negative 2, we have a relative min of negative 2, negative 30. If we look at our sign charts, to the left of negative 2, we were doing two things. We were decreasing, and then we were concave up. So decreasing and concave up means my graph goes like that. Once we got past negative 2, we started increasing from 0 to 2. So from negative 2 to 0, we were increasing. But then at okay, so we were increasing from negative 2 to 0, but then we stopped being concave up at this first inflection point. So we have this inflection point right here, a little bit past negative 1, and we were down at 16, a little bit there, and then we were increasing and still concave up. But then right there, we changed concavity, and now we're concave down, but we're still increasing. Okay. And then at 1, we got negative 3, which is going to be right around there. But at negative 1.25, at 0.5 in the middle, we change concavity again. So that's going 0.5 right in the middle. We're at negative, so we're around right there. And that whole time we were concave down, but then we switch concavity. And we need to join it with the concave up. And then once we get past negative, so 1, negative 3, then from that point on, we are increasing and we go back to being concave up. And that's what my graph should look like. You can verify that on the graphing calculator, which lots of you chose not to do. You have a graphing calculator. You can check your work to make sure that your work matches. You should change your window. The interesting behavior on this really happens in between negative 4 and 4. Your X scale is fine at 1. Your Y min, though, you have to go all the way down to negative 30 to get that. So we'll go negative 40, and we'll go to 40, and then we'll go up by 5. And that matches pretty good to what I see on my graphing calculator, right? And so there you go. Now problem number 5. Use calculus to give a graph of the function and identify the locations of all the critical points and inflection points. In problem number 4, I walked you through the steps. In problem number 5, I just asked you to use the calculus. right? And so you're just going to go through all the same things we just did, but I didn't walk you through the steps, right? So we need to look at the first derivative. So these are just power functions. 1/3 times 6 is 2. Take 1 away from the exponent, negative 2/3. 4/3 times 4/3 times 3 is 4. Take 1 away from the exponent, x to the 1/3. So for my sign chart, I need the numbers that are going to make this undefined or 0. Because of this negative exponent, without doing anything, you should realize that 0 is going to make it undefined. So 0 is a critical point. My derivative is undefined there. Next, I need to see what makes it 0. We could factor here to figure that out. You could set it equal to 0 and then do the algebra. When you factor, you should factor out the smallest exponent. So we can take out a 2 and then an x to the negative 2/3. And when we do that, then this will just be 1, and this will be plus 2. And then what exponent do I need there? Well, this negative 2/3 plus whatever exponent I put here needs to give me 1/3. And so that would be 3/3, which is 1. If you back distribute, the 2x to the negative 2/3 times the 1 is the 2x to the negative 2/3. The 2x to the negative 2/3 times the 2x to the 1, you would multiply the 2 and the 2 to get the 4, and you would add the exponents. 2/3 plus 1 is 1/3. And now you can see that this expression here is always positive, because what that means is the 2 over the cube root of x squared. So that's always positive, right? And this expression here, the only thing that makes that 0 is negative 1/2. And so that means then that to the left of negative 1/2, this will be positive. But if you put in something like negative 1, this will be negative. And so then you have a positive times a negative, so you get a negative. Once you get past negative 1/2, and then you get this one will change signs, and you get a positive times a positive. So you get a positive. And then once you get past 0, this one stays positive. This one's already switched. This one is always going to be positive, so it will be positive. So no, when you make your sign chart, it doesn't always alternate, right? You need to be careful with that. Just because you have two critical numbers doesn't mean it's going to be negative positive, right? So we can see that we're going down and then up. So we have a relative max at, a relative min at negative 1/2. Nothing really special is happening at 0, but my derivative is undefined. So that since that my derivative is undefined, that means we have a vertical tangent line there. We have a cusp or a corner there. Actually, no, we don't have a corner. We have a cusp, because as you get closer and closer to 0, this expression here goes off to infinity. So you have a cusp there. Okay, so there's your first derivative test. Now let's look at your second derivative. So then again, you're going to bring down the exponent, negative 4. X to the negative 5/3, take away 1. And then plus 4/3 x to the negative 2/3. Again, 0 makes it undefined. And again, we'll factor out the smallest. And so then over here, you get negative 4 thirds. I'll factor out the negative 4/3. And then you could ask yourself, negative 4/3 times what? will give me x to the negative 5/3. I'm sorry, we're going to factor out the smallest exponent, x to the negative 5/3. And now you can back distribute and fill in what you need. Negative 4/3 x to the negative 5/3 times what will give me this x to the negative 5/3. And you can see that you will need a 3. The negative 4/3 times the 3 will cancel out the 3, and you have an x to the negative 5/3. You bring that in, you'll have your x to the negative 5/3. So you will be good. And you factored out the x to the the negative 4. So now this has to be a minus. And so you took out the 4/3, so then you don't have that there, you just have x. And you want to end up with a negative 2/3, and you're bringing in a 5/3. So you want the negative 5 plus whatever I put here to end up being negative 2. And so then the negative 5 plus this needs to give me negative 2, which will then be positive 3. But that then makes 1. And again, now you look at the sign chart of this. And this is for your second derivative. Again, this factor right here is going to be undefined. On your sign chart, you put everything that makes it undefined or 0 when x is 0. And this factor over here is going to be made 0 by 3. And there you go. Okay, so if you pick something less than 0, like negative 1, then this factor is going to be negative 1 to the negative 5/3 is going to be a negative number times a negative number. This will be a positive. And 3 minus negative 1, this will be a positive. And so then you multiply those together and you will be a positive. So you will be concave up there. And then once you get past 0 and you put in a positive number, then this expression will be negative. And this expression will stay positive. And so then you will get a negative number there. And so then that is negative, and so it'll be concave down. Once you get past 3, this will stay negative, and this one will switch and become negative, and so then you will have positive. And so there you go. So we can make a decent graph of this with 3 points. All we're going to need is 3 points. I expect to see a table. We just need negative 1/2, 0, and 3. You can just put the formula into the calculator. And when we put in negative 1 divided by 2, we get 3.572. Negative 3.572. Of course, when we put in 0, we get 0. And when we put in 3, we get 21.634. think I made a mistake there, and I erased it, so I can't see it. I think that should have just been 1. So when I factored that out, we would get negative 4 x to the negative 5/3, and then this should be negative, oh, I factored out negative 4/3. And then, oh, this should be 3. Nope, that's right. Okay. Okay. So, so at negative 1/2, so there's 1, there's 1/2, then there's 1, then there's 2, then there's 3. So at negative 1/2, we're down here at negative 3. To the left of negative 1/2, we're decreasing and concave up. That's what that says. And then once we get to negative 1/2, we start increasing and we're still concave up. So once we get to past 0, we keep increasing, but then we are concave down. And we have a vertical tangent line right here. We don't have a cusp, we just have a vertical tangent line. And then once we get past 3, we switch concavity. So there's an inflection point right there. At 3, we got 21. And so then we take off in that direction. Looks a little different than what my calculator graph looks like because I drew this more curvy, but it's close. A couple things we should fix. We should fix that right here. This is a vertical tangent line. So it should go like that. But the calculator does not pick up the changing concavity, the inflection point here, and so I've made it obvious that it's changing, that it's now concave up. Doesn't look very obvious there. And also over here, I made it obvious, but that's what the graph looks like. Okay. Last, problem number 7. Find the absolute maximum and minimum values of f, if any, on the interval and state where those values occur. Make sure you give a calculus justification. So you're looking at a continuous function, but your interval is not closed. So a continuous function on a closed interval is guaranteed to have an absolute max and an absolute min, and you also know where to look. You look at the endpoints and at the critical points, right? This is not that because it's not a closed interval, but we can still look at find the absolute maximum and absolute minimum values of f, if any, on the interval and state where those values occur. So you should notice that your interval is ending here at -1, and that -1 is a 0 of the denominator and not of the numerator. And so then that tells you that at -1, you have a vertical asymptote. You should also recognize that if you're using numbers bigger than -1, then this expression on the bottom will be positive. And then this will always be positive. So that means that as you get closer to -1, you are going off to positive infinity, right? And so then if you're going off to positive infinity, you do not have a absolute maximum. There is no absolute maximum because you can just keep getting bigger and bigger as you get closer and closer to -1. But that doesn't mean we don't have a relative minimum, right? I'm sorry, an absolute minimum. So again, what we should do is look for the critical points. and see what's going on there. So f prime of x is equal to, okay, so quotient rule, derivative of the top, 2x, bottom left alone, x plus 1, minus the derivative of the bottom, 1, times the top left alone, x squared plus 4. And you should make sure that you keep those parentheses right. So then when we distribute, we get 2x squared plus 2x minus x squared minus 4, all divided by x plus 1 squared. Now, -1 is not a critical point of interest because it's not in our original domain. But when we clean this up, we end up with x squared plus 2x minus 4 over x plus 1 squared. Okay. If you try and factor this, it's got to be x and x. It has to be plus and minus. And it's either 2 and 2, which would not give us a middle term, or 4 and 1. And with 4 and 1, we would get 3. So this does not factor. So then we need to find the critical points by setting this equal to 0, x squared plus 2x minus 4 equals 0. You can use the quadratic formula, but because the first term is x squared and the middle term is even, solving by completing the square is going to be easier. So we add the 4 to both sides because that 4 is not making this a perfect square. But then if we take half of this number and square it, and whatever we do to one side, we do to the other, then we make a perfect square. This is why this is called factoring by completing the square. So this is now a perfect square, and we can now factor it as x plus 1 squared. And this is 5. And so then we get x plus 1 is equal to plus or minus the square root of 5. So then x is equal to 1 plus or minus the square root of 5. But you're only looking in the interval from -1 to 5. And so if you do 1 minus, you'll be outside of that. So it's not that. It's 1 plus the square root of 5. Okay. And so then, again, when we look at the sign chart for the first derivative, then the denominator is always positive except where it's undefined. So we could put -1 on there. And then 1 minus the square root of 5, I punch that into the calculator and I get -1.23. Again, that's not outside, that's outside the interval that we're looking in. And then over here we get 1 plus the square root of 5. .23, which is in the interval. So then we have the 3.23 over here. There we go. And we are ending this at 5. But if we were just looking at this expression without any restrictions, then the bottom is always positive except where it's undefined. To the left, because of the square, this will be positive, and then it will be negative. And then once we get past the other 0, it will be positive. And you can see that at 1 plus the square root of 5, you're going down and then up. Relative min at x equals 1 plus the square root of 5. But there's only 1 in the interval that I'm looking at. Since there's only one relative extrema, therefore absolute min. As I said, there is no absolute max because at -1 you're taking off to positive infinity. But you can see that you were going down and then up, down and then up over the interval from -1 to 5, and so you have to have an absolute min. And so then again, your absolute min is find the absolute min. So f of 1 plus the square root of 5, which is 1 plus the square root of 5 squared plus 4, all divided by 2 plus the square root of 5. And there you go. And that is it.